Many of you were at the USMA conference and saw this same presentation there. So if you're hoping for something different, sorry, Jerry. I love it. It's the same one. It's awesome. All right, so this presentation is about the McDougall Pond failure, the outfall from that pond. And to start out, I just want to talk about a phone call that I got back in May of 2010. And just sitting at my desk, got a phone call like you would any other phone call that day, and I was told that a pond that I had designed had failed. So I just want, now there's a lot of engineers in the group here, so I just want each of you to think about something you have designed if you're an engineer, or some work you've done if not, and think about something that had importance to the public safety, and think about getting a call like that and how that would feel. You know, what feelings that would elicit from you. You know, I felt like I'd been punched in the gut. You know, the dry mouth, the just wild eyes, oh my gosh, what happened? Thinking about what am I going to do? You know, and how is this going to resolve itself? So just want to give you a little bit of background data about this situation and what happened here. The project was the SR68 Design Build project. Lochner was the design lead firm on the project. Our geotechnical engineers were IGES, and the contractor was Geneva Rock. One thing about this particular pond location and the project in general was that the environmental document had identified a lot of the pond locations and had specifically, pointed out where those would be. However, when it came down to it, when we started talking to property owners and trying to figure out, hey, is the pond going to work right here? What we quickly realized is a lot of those locations were in areas that they felt was prime developable real estate. And so we had to go and look at a lot of different areas or different alternative locations for each of the ponds. And specifically this pond, the McDougall Pond, was particularly problematic. And so what we ended up doing, as you can see in this figure here, is we had to design the pond on a very steep hill, and we had to break it into two segments, or two sections. And so here you can see the pond. The top pond, was about 6 foot overall depth, but 4 1/4 foot of working storage. The pond itself had about 1.5 foot of acre foot of storage. The lower pond had about an acre foot of storage. We had them connected with an emergency overflow, and also you can see this pipe that also served as a connection between the two ponds. For the outlet structure at the upper pond, we designed basically just a concrete structure with some hooded orifices. The one was about 1.5 foot off the pond bottom, and the second one was about 2.5 feet above the pond bottom. And then you can see we had about a 5-foot section of perforated pipe that was in drain rock, and that was to drain the lower portion of the pond below that first orifice, hooded orifice. And then had it resting on a couple feet of untreated base course, kind of as a leveling course for the outlet structure. The actual pipe itself was fairly steep. As you can see from this figure, from the upper pond to the left to the lower pond on the right, the pipe was at a 16% slope. And if you've ever designed pipe or put in a design such as this, you know that is pretty steep for a pipe, even in a situation where it's not connecting two ponds. You can see at the bottom there, it hit another kind of a clean out box before it emptied into the lower pond. And this pond went into operation back in October of 2009. So then 7 months later is when I get the phone call and understand that something has happened with this pond. I wasn't quite sure at the time. But what happened was that on May 24th of 2010, there was a rainstorm, and the pond filled up with about 2 feet of water. And so maintenance forces or the construction inspection crew, they were out looking at different ponds related to the project just to see how they were doing. The pond had only been in service for about 7 months, and so they wanted to see, okay, how are things going now that we've got some rain and these ponds are starting to operate. And so they went out about 7 a.m. in the morning and had noticed that at the bottom of, let's see if I can go back to the previous slide, there at the bottom of the pipe that connected them, they noticed there was some leaking right next to that bottom structure. And 5 hours later, the entire thing had washed out. And so I want to show, but fortunately they were there and were able to capture video of that event. So I just want to show a little clip of that video for you. And it was taken with a cell phone, so it's not super clear, but I think you can kind of get a sense of what happened with this pond failure. So you can see right now there's a lot of water coming out from the bottom. When they first got there, it was just small leaking, but eventually it progressed to this. You notice in some of the pipes that was that actual connection actually shooting out of the trench at the bottom. You can see that water is hitting that lower structure. That's kind of what's making it jump up a lot. So this kind of is a view of the lower pond. You can see sticks of pipe and mud and silt and water filling up the pond. And if you notice that initial, you could see how far up the slope that failure had gone. Later on, as they pan back up there, you can see how it's progressed even further. So here, keep in your mind how much of that trench has failed or fallen into the pipe zone and washed out. And then as the video progresses, there's kind of a break, and then the clip will again pan back up, and you can see how much additional material has washed away. So you can see now there's even further up, there's additional material that's fallen into the pipe zone. So this is the video that they sent me later after the phone call. And so didn't really help to calm my nerves at all. But I realized that, okay, now, we got to figure something out. And so as an engineer, the first thing I wanted to do was to figure out, hey, what happened here? Let's get out on site so we can get eyes on the situation as well. And so we went out the next day and took some photos. This photo was actually taken by the maintenance crews. You can still see that there's some water washing down through the trench. You can see up where there's some arching of the actual berm of the upper pond that's still in place, but you can see daylight basically up into the upper pond where most of that material has washed out. The following day we went and took this photo here. You can see that most of the material has been scoured out. You can see that there's been some of the walls adjacent to the trench have collapsed and fallen back into it. So it looks a little rough, but it was scoured pretty clean initially. This is a picture of the lower pond the day of the failure, and you can see all the pipe that used to be connecting the two ponds out in the pond, along with a bunch of silt and mud. The actual volume that washed into that lower pond was about 0.4 acre feet. So if you recall earlier, I said that the actual volume of the lower pond or capacity was about an acre foot. So we still had a little bit of freeboard there on the failure. But imagine if we hadn't had that second pond. I mean, there's a canal that is probably, I would say, 50 feet to 100 feet within the bottom of this lower pond. So if it had just failed and gone downstream, it would have basically got into the canal, and then who knows what would have happened. So kind of dodged a bullet with that one, but we felt pretty lucky. So here's a picture of that lower pond. The following day, you can see most of the water has seeped out or has been taken out through its outlet structure. So here's a photo of the upper pond, and it shows a hole where the outlet structure used to be. The next picture shows the trench where the outlet structure was. And what's interesting about this is that there's not a lot of material loss. You can still see some of the scrapes from the backhoe on that excavation zone. And what was interesting is that the native material was actually really tough. Most of the failure carried out all the backfill, but left, interestingly enough, most of the native in place. You can see there's hardly any scour. And for those that are interested after this discussion, it's a dirt bag, really, is what that is over there. But if you want, come up and there's a chunk of that native material in there that also has some of the, once it's disturbed, what it looks like and how fine it is. And so I think part of what we're looking at is how we treated the native versus what we use for the backfill zone. So this is looking now down towards the lower pond through underneath that arching soil on the upper pond berm. And again, you can still see that not much of that native undisturbed soil got affected at all by this failure. And again, looking deeper into that zone, you can see almost vertical sidewalls there. Hardly anything was disturbed at all. So very interesting, when we got up there and kind of saw what had happened in the aftermath of that failure. So, the next thing that we needed to do was kind of figure out, who we need to talk to, what's going to be the fix here, get a team kind of mobilized to help out with this. So I called Dennis Stuff at UDOT Hydraulics. And for those of you that remember Dennis, he was just a walking encyclopedia of knowledge. Had great information, sent a couple of publications over to me that were very helpful in understanding this type of failure. And also talked to Central Geotech, got some input from them. Our geotechnical engineers went out, did a site visit. Some of the things that they noticed initially was that in the pipe zone there was what they called a friable sand layer. They also noticed that a lot of the material, once it was disturbed, was dispersive in nature. And so, that was kind of a concern. Had some questions on, what the compaction was in the pipe zone. However, when we talked to the inspection team, they said, unfortunately, this pipe was not in the lot that we had for taking compaction tests on. And so it didn't have any tests, it was just visual inspection. And so and all the evidence was washed away, so there wasn't really any way to figure out how good the compaction was or to really assess that issue there. And then we also had our geotechs go and take additional borings. I mentioned earlier that the right-of-way for this particular pond was kind of an issue. And we had geotechnical information at the location that was identified in the EIS, but when we had to move that pond, we did not take additional borings in the new location. And so the geotechs will tell you this all the time. You can't, the information you get from a geotech is good for one, however big the hole of that diameter hole is that they bore, right? Beyond that, you can't, there's no guarantees. Well, we learned that definitely applies in some areas because the geotechnical information they got at the new location was definitely different. So some of the things that we kind of learned with this pond were that conduits, they're basically a potential failure location. That interface between a conduit and the soil, if you don't get it right, you're going to have all sorts of issues. And the reason is because it's a discontinuity. And what happens is that you can have what's called a hydraulic fracture. What happens with hydraulic fracture is that if the water pore pressure in the soil is greater than the resisting force of the soil itself, then you could have small fissures open up. And what that means is then you're opening up kind of a conduit on the outside of your pipe for water to pass through. And when you have dispersive materials, that means that those can be carried easily. And so those can be carried along the outside of the pipe, introducing that piping failure, moving material out of the zone, and eventually resulting in the catastrophic failure that we saw here today. And what happens as well, other mechanisms that we found were there's what they have is differential settlement. And there's two things that kind of lead to this. One of those is if you have a different compactive effort in the pipe zone itself versus a berm. Now ours was a little different because we just had a trench, right? But if you have like a dam or a pond that's built up, if the pipe zone itself is compacted differently than the actual berm, then it can result in differential settlement because you have different material densities adjacent to each other. So that's one way. And then the other way is just if you don't get enough good compaction around your pipe. For those that have seen, you've got your round pipe sitting on, the ground. There's this area underneath the pipe. It's called the haunch. Getting compactive effort under that area is really difficult. It's really a challenge. And you really have to focus on making sure it happens well. Now, if you don't get good compaction under, for a pipe that's maybe, a storm drain line out in not a very, important road, and that, doesn't have the compaction it needs. If that fails, you might get a pothole. It's not a good thing. You don't want that. But you're not going to get, an acre-foot of water washing down the hill towards someone's house. And so, there is kind of a difference between pipes that are installed in the roadway, under a road, and pipes that have head that can develop on those, where the failure of that pipe could either wash out a road or could lead to a bunch of a deluge of water, going down towards someone. So that's something to keep in mind. The other thing that we learned or investigated that was kind of a lessons learned for us was just the pipe installation itself and what you do for the inspection and what the failure mechanisms that could occur with pipe. Because when pipe's transported, it's if it's moved on and off of the transport vehicles, it's moved around the job site, putting it in the trench, pipe can easily be damaged, and it needs to be something that is watched. The other thing is when they're installing the pipe, if the joints aren't put together well or if the gaskets get damaged, those can be potential failure mechanisms as well, because you can have leaking from the pipe out into the pipe zone area, backfill area, and that water can then carry material back into the pipes, carry it out through that, and open up these piping conduits on the outside of your actual pipe. So aging of a pipe can also cause issues if you've got any sort of corrosion or any sort of damage that happens over time, whether it's a scour or even collapse of a pipe that's just aging. So that's something that you need to keep in mind. So some of the things that need to happen in order to prevent this type of failure include that your backfill obviously should be free of dispersive materials. For this type of a pipe system, it's highly recommended that you use import materials or that you have sufficient testing on the native materials to ensure that you have good backfill material. That's one thing that did not happen in this case and was probably a contributor to the failure that we saw. The other thing is did you have a question? I would suggest the whole trench. Because just above the pipe doesn't necessarily take care of the issue that we saw. Because if you notice, the berming over that pipe trench at the very top, where the berm for the upper pond was, that material held. It arched over. It didn't fail. But the piping itself was what carried up through the pipe trench zone. And so it's the pipe trench zone that you're really concerned with. You want to make sure that it doesn't fail. Right. This was ADS pipe. It may have. Different types of pipe can be compacted around more easily, but it all depends on inspection sometimes. Because in theory, you're supposed to get good compaction around any type of pipe, and that's why as a department, we basically call out smooth lined or corrugated. And the pipe type itself is then determined by the contractor. As designers, we don't typically call out a specific type of pipe, but in situations such as this, it may be a consideration. Was there a question right here too? No. It washed out. Yeah, if you recall one of the pictures, it actually washed underneath the berm for that upper pond. So, yeah. So, other things to consider, with that backfill material is plasticity. You want to keep, that in mind because that's highly tied to the hydraulic conductivity of the material, and so you want to ensure that you're trying to prevent some of that. And then it's always good practice to install the pipe at the same time as the embankment. That way you can ensure consistent compaction across both zones. And then obviously, inspection control, ensuring that you have tests. I would recommend that any pipe that has the potential of releasing a large amount of water, such as the pipe outlet from a pond, have compaction testing, just as a standard rule. Beyond what we have is kind of the lot system of ensuring that we have kind of some testing, but not all testing.
I think on this particular application, it was the difficulty of testing it on a steep slope on a grade like that.
Right.
It probably says we've got enough tests elsewhere.
Right. Well, and when I talked to the inspection crew, they said, hey, the road is really our primary focus. This is kind of an off-road pipe, doesn't have the same importance. And to be fair, I mean, that when you just look at it at face value, that may seem, a reasonable type approach. However, knowing what we know now with, if you're impounding a bunch of water, you've got a hydraulic head, a driving force already in place that could push a failure down through that pipe zone. You probably do want to put this on a higher priority list.
With piping, that's easy to say after the fact.
Right.
Putting like rings around the pipe, like
Kind of anti-seep collar type stuff.
6 inch or
Right.
rings around.
Right.
It may want to reduce if you stop your piping so water gets close.
Right. And I'm actually going to talk a little bit about that. That's a good point. And so these are some of the lessons learned, the preventative measures, this could be, some of these anti-seep collars. Another thing that they have are these filter diaphragms. I'm going to get into those in just a little bit. And so just to kind of talk about the failure or why it failed, kind of to wrap up some of these. So poor compaction could have been one of the issues. However, everything was washed away. We had no compaction records, so we don't know. The dispersive backfill soils, yes, probably contributed to it quite a bit. The friable sand layer, probably not. I mean, if you look at the side walls of the trench, there wasn't really much evidence that failed, and so that sand layer, would have not necessarily followed the slope of the pipe trench itself, and so it's hard to say. My gut feel is that it probably did not contribute to the failure. However, the outlet structure, if you recall, we had the drain rock below the surface of the pond. We also had it sitting on untreated base course, and so with that, it did provide kind of a way for water to get from the pond to the pipe zone. So probably didn't, cause the failure, but was probably part of the failure. But in the end, all of these probably contributed in some small way to the overall failure. But to really nail down which element actually caused the failure, we really couldn't say. We didn't have enough data. So what we ended up doing is that we determined that, well, we're probably just going to need to put in another pipe. Our geotech said, yep, you can put that pipe in at the same slope. They recommended anti-seep collars. So we put in 6 foot by 6 foot, 1 foot thick anti-seepage collars, 3 of them down that zone. And we made sure that those were put into undisturbed material because you saw how tough that stuff was. And then we replaced this pipe and just put it in at the same slope. But the backfill was the difference. It was not backfilled with native materials that had the dispersive material in it. It was backfilled with imported material with 20% fines, had a liquid limit less than 25 and a plasticity index less than 15, and that was in order to limit the hydraulic conductivity. They ensured that it was compacted to 95% of standard Proctor, and then also ensured that it was within 2% of the optimum soil moisture content when they put it in. So a lot stronger look at that. And then we also had them put it in at maximum 12-inch lifts. Now, I think that's standard practice, but sometimes when it gets put in, I don't know how many have been inspectors out in the field, doesn't always happen. 12 inches, sometimes. Right. Exactly. So keeping those layers at a consistent depth that can be compacted and the effort can be put into it is one thing that you really want to ensure. And Savan, did you have a question? So I believe we just called out smooth again, and I don't remember. I remember when I read back through this has been 5 years ago. My memory is really bad, those of you who know me well. But when I was reading through it, I know that we talked about using RCP because you could compact easier around it, but I'm not sure if we actually did RCP. I don't recall. Right, right. Right. It's harder to get that level around other pipe types. Yeah, I don't remember, and that was one of those things when I looked at it, I was like, dang it, I wish I could say definitively, but I just don't know. But the other thing we did is we decided to say, hey, or decided to incorporate keyways. And so we put the trench at a 1-to-1 slope, and then introduced these little keyways, keyed-in edges, both horizontally and vertically, in order to make sure that they could put in each subsequent layer on a horizontal plane. Because compacting on a slope just does not work. And so when you have a steep pipe like this is really something to consider, is having these keyways and allowing that the contractor to be able to come in and compact on horizontal planes, because then you can really ensure you're getting good compaction.
Was there, when you were looking at release the replacement, was there a discussion of just doing really deep blocks so that your outfall height would say 8.5%, but your box, your outfall structure for your top bunk would just go really deep?
Right, so it's more like a drop structure. You know, at the time we didn't. That is another consideration, though. It's an option to use in a situation like this. Right, right. You know, and I know with a lot of the design build projects, and I'm not sure if the new manual is going to include this, but there are limits to the velocity, the design velocity in pipes, and sometimes it does push you to something like that, where you have to have kind of a drop with an outlet structure. Because pipes, I mean, it's 16% slope. I'm sure the velocity in this, if I ran it, would probably be 25, 30 feet per second, something in that range. Is it 12? Right, it's really steep. Right. Yeah. So yeah, all of these are definitely good considerations for how this should work. So, you know, so that's kind of what we did with the backfill and the trench design. The outlet structure we placed on native, undisturbed ground. Took out the UTBC, and then instead of having the perforated pipe in the drain rock, we had weep holes at pond level, and so then there wasn't anything below the structure that would be kind of a pathway for water in the pond to make it to the trench zone. So that's how we fixed that. And then obviously we had to clean up all the sediment and take care of all that. So those of you who like to get around on Google Earth, I think we all do. Here's a shot from Google Earth forever memorializing my failure for all to see. Now, it's not the current shot. You have to use the time lapse, go back in time thing, but it's there. And so it's funny that, between the time that it failed and we actually got in there and fixed it, that's when Google decided to take their picture. Yeah, that's the luck I have. So, but today you can see that pond, it's been 5 years now. It's been in operation the entire time. Haven't had problems with that outfall pipe now. You can see it's filling in, and things are kind of getting better in terms of the disturbance. So that's what it looks like today. So just kind of to wrap things up, and this is like the quickest presentation ever, but you guys all want to be out of here by 5 anyway, so no one wants to stay till 5:15, right? Right. That's what I was banking on that. But I did want to talk a little bit about this, the anti-seep colors, the filter diaphragms, and then maybe a little bit more on conduit considerations. So these are the two documents that Dennis actually sent over that I was able to read through. And it was interesting because on the front page of the first one was a picture of a pipe with anti-seep colors that had completely failed. I was like, well, wait a second. Do they work or not, you know? So here's what's interesting about anti-seep colors. Is that, but first of all, let me define internal erosion, that definition right there. Internal erosion includes all seepage processes in a trench zone except that backward erosion piping that the video showed. Okay? So anti-seep colors, they work for internal erosion. But what they're not really good at is they don't address the more serious problem of flow through cracks in compacted backfill around conduits. So if the compaction's really good, see, the theory behind anti-seep colors is that it's going to take care of lengthening the flow path. So if you got a pipe, it's got a distance to go from the top end to the bottom end. Anti-seep color means you have to go around it, right? And it lengthens that flow path. So in the saturation zone, it makes sense theoretically that those are good practice. However, they don't work if you've got that hydraulic fracture. Because what happens is it just fractures around the seep color, and then you've still just got an open path. So it's not the inner granular flow or between pore spaces that you're concerned at that point. It's that you've got an actual opening for water to flow around. In fact, the Bureau of Rec, Army Corps of Engineers, NRCS, they all stopped using anti-seep colors back in the 80s. The 1980s, I guess I should say. Yeah, I guess we're not that far out, but yeah. So they have not been using these we're close to 35 years now. Very, very long time. So, but what they do use is what's called this filter diaphragm, and what a filter diaphragm is it's basically just a big wall of sand that intercepts that saturation zone and enables you to take the water without taking soil with it and then pipe that out or have a mechanism, whether it's a pipe or another sand filter, to the toe of the slope. And so then that relieves the water pressure, that driving force above the pipe, and takes it down to near zero at the toe of slope. And that toe is what's really keeping the entire embankment in place. You start losing that, you could lose the entire embankment. Now, so the question in everyone's mind right now is, well, okay, Jeff, you're telling me that these things are great. Why didn't you use those on your fix? You use anti-seep colors. We saw what you did. Well, NRCS also does not recommend using filter diaphragms on small dams. The reason being is because of the increased engineering and inspection that's required to actually make sure these things work. Because it looks real simple right here. I can put it up there and talk about how the process works. It seems super simple, but it actually takes a lot of engineering effort in order to appropriately design that interface between your backfill material and your filter diaphragm. And so they really only use these for large dams. But when they are used, they are very effective because they have reduced the number of failures due to piping dramatically. So it's really good practice to use this type of material for those. Now with detention ponds and what we do, they're too small. Unless you have a geotechnical engineer that really knows their stuff, has a lot of experience designing earth-fill dams, you probably don't know enough to design this adequately, or to have the specifications written to ensure the inspection is adequate to make sure it works, and could cause failures itself. So, let me just wrap up with just talking a little bit about other conduit considerations. So I mentioned, some failure mechanisms can be some of the joints, could be gaskets that were damaged, things like that. One thing to consider would be, in situations like this, is maybe using something like a thick-walled or a solid-walled butt-fused HDPE. You've got the strength in that type of material, you're taking out the joints, you're not having gaskets in there, and so that's going to reduce, and they're really resistant to abrasion, they're really resistant to any sort of hot soils that would cause corrosion to your pipe material. So that might be something to consider if you're designing a detention pond that's going to be developing head on your pipe. The other thing is looking at that haunch area, that bottom zone underneath the pipe, and how you get compaction in there. You know, one mechanism that could be considered is to use flow fill. Obviously, you know, floating your pipe is a concern if you're using flow fill in the backfill zone, but most contractors have used it in a number of locations. I mean, it's a quick, easy way, you know, self-consolidating or self-compacting backfill material. So they know how to either, you know, do it in lifts or to keep the pipe, you know, anchored down so that it doesn't float on you. But that's also a good way to do it. Another thing that you could consider are what's called pipe cradles. And those are a way to basically kind of form that area beneath the haunch that would actually accept the pipe itself in order to then just compact adjacent to that, and you can really pound in your dirt right next to it. So that's another way to try and ensure that you got good compaction around the pipe. So anyway, those are some of the things that we learned, lessons learned. I don't know if there's other questions. We had a number of them earlier. I appreciate your feedback, but
Yeah, you can tell about the pipe in Holly Creek though. But when you put a new pipe there, you have some kind of block between there, like in section how many mile, like about a mile long, right? You do, and then each section there you block with the concrete, right? That's what I recommend you because the underground water will go through the pipe, right? Did you design that way that time?
I'm trying to remember what we did on that one. Did we have kind of just a place where we,
So it's so slow. They have a lot of slope there in Holly Canyon there.
right, Parley's Canyon?
I recommend you to
I'm not remembering if we did that or not.
a lot of gravel very close
Right.
to the pipe, right?
And a lot of that,
Each pipe there.
yeah, I don't remember if we did that or not, Savon. We may have, yeah. So it'd be more of kind of like a bottom cutoff. I mean, one of the things in Parley's that was challenging was that pipe was metal pipe, and so it had seen a lot of abrasion and corrosion, and so it had lost the bottom in a number of locations. And then it also had a lot of like holes adjacent to it, even above. I remember walking through the pipe and seeing water just squirting down on us, you know, because of the pressure of the water outside the pipe zone. And so there was a lot of interplay between water in the pipe and on the outside of the pipe. Now the difference with Parley's is that a lot of the soil on the outside was super rocky. And so even though there was, I mean, you could look in and you could see voids, you know, but it was filled up with large rocks. And so there was still the structure holding it, even though the fines had migrated out. So there were issues with that pipe, and obviously I think, you know, replacing it was the right decision. And so now with the pipe being concrete and having, you know, tight inspection control and put in, you know, with a lot of like curvatures to avoid issues and kind of keep it where it needed to be, I think you got a good product there now. So, Jeff?
I wanted to mention when this project was constructed, the specification allowed the use of native material, acceptable material. We no longer, UDOT has changed our specifications to not allow native material. It requires imported material
In all locations for pipe?
unless the contractor can elect to provide an engineering proposal if they elect an alternative.
Right, if they test the native and determine that either through mixing or just alone, it's good enough to use. Right. Yeah, so, and that's good because, you know, that would have changed this whole situation. You know, I mean, you can see it's been in place now for close to 6 years, and with imported material compacted correctly, it's operating fine. But that native material was just not good stuff. So, all right, any other comments or questions? All right, you guys are getting out early. Thank you.